Precalculus, Chapter 3, Section 5, the exponential growth and decay. And this is part 2 of the notes. So let's start with example 14. The half-life of, I'm not sure how to say that, strontium 90 is 28 years, meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. Find the exponential decay model for strontium 90. I'm sorry if I'm butchering that. So we want to find out when the ending amount is half of our beginning amount. So we can start by dividing by the A naught and then switch into log form. So we have the natural log of a half equals 28k. And then divide by 28. So our k value in this situation is negative 0.0248, and we can plug that now into our decay model. So let's find out if there are originally 60 grams of this, how long will it take for that to decay to a level of 10 grams? So we'll plug in 10 as our ending amount, 60 as our beginning amount, and then use the k value that we just found. So we'll divide by 60. And then we'll rewrite this in logarithm form, so it's a natural log. And I'll keep the 10 over 60 in fraction form because I don't want to round yet. And then divide by the decimal. And when we do, we'll see that our time will be about, so I'm dividing, good, about 72 years. A little bit over. So it was like 72.2 or 3, and so a little bit over that. Now let's look at example 15, using Newton's law of cooling. So an object is heated to 100 degrees. It's left to cool in a room that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees Celsius. Use Newton's law of cooling to find a model for the temperature of the object T after little t minutes. So we have our cool temperature equals our room temperature plus our initial temperature minus our room temperature times base E raised to some constant K times our time. And so here I've got it for you labeled. And in this situation, you can see where each value would go. So 80 degrees is our cool temperature. 30 is our room temperature, that's C. Plus 100 degrees is our initial temperature, minus 30, and then our time is in minutes. So now it says we're going to find a model for the temperature. So we're going to plug those values back in, and we're going to solve for K, because we're plugging in 5 for small t. All right, so let me talk about, the first thing we want to do is subtract the 30, which gives us 50, and then do our subtraction in the parentheses, which gives us 70. Now we're going to solve like we have in the many problems earlier in this section, where we isolate our exponential expression and then rewrite this as a logarithm, as a natural log. So the natural log of 5/7 equals 5k. Divide by 5 after taking the natural log, and our k value, and it makes sense that it's negative because this is a decay situation, is negative 67 thousandths. So now we can plug in that k value into this formula. What is the temperature of the object after 20 minutes? So it's the same situation. So our numbers are going to go in the same spot. So that temperature equals the surrounding plus the initial minus the surrounding times base E raised to that negative 67 hundredths times 20 in this case. So you can just do the math, and you'll get that the temperature will be in about 20 minutes cooled to around 48 or 48.3 degrees Celsius. So now same situation, but when will the temperature of the object be 35 degrees? So now we're going to plug in 35 for T, and that will equal our surrounding, which is 30, plus our initial minus our surrounding, times base E raised to that constant times T. So again, we'll subtract 30, this time getting 5. Then we'll divide by 70 and rewrite as a natural log. Take that natural log of 5 over 70 and divide it by your decimal. And the time, just make sure it makes sense with the situation. Yeah, it'll be a little longer for it to cool down to 35 degrees Celsius, so about 39 minutes or 39.3. Now sometimes you might want to express just an exponential equation as base e. And so the exponential equation y equals a times b to the x is equivalent to y equals a times base e raised to the natural log of b times x. So let's look at this situation. Example 16. Rewrite y equals 4, that's our initial a amount, times base 7.8 raised to the x in terms of base e. So 4 is our a value and b is 7.8. So using that formula, y will equal y will equal 4 times base e raised to the natural log of 7.8 times x. Now we can simplify and go ahead and take e and raise it to the natural log of 7.8 and take that, which will give us e to the 2.054, and instead of t, I need an x there with the 4 out front. All right, this concludes part 2 of the section 4, chapter 3 notes, exponential growth and decay.